All right, line V1, learning test 7, we're going to take a look at a Wye-Delta type of starter. Now, Wye-Delta starter is a really fun starter because what it's able to do is it's able to go and take all of our leads from a motor and we're able to go and reconfigure them when we are, excuse me, operating in Y over to when we're going to be operating in Delta. Now, this is base three-phase theory. You should be quite familiar with this from everything that we covered over in, the very first learning test that we entered into in third year here, which is really that when we take identical loads and we reconfigure them from Delta to Y, or from Y to Delta, we're going to go and see a change in the total amount of kVA that they are going to go and deliver. Note that this is only something that applies on loads, right? When we're talking about an actual alternator, we can reconfigure the coils so they can be Y or Delta. When we're delivering power, we can reconfigure alternator coils so that they can go and deliver the exact same amount of kVA in Y or Delta. But when we're dealing with a load, which is a passive device, it's not active, it's not generating anything, it's just resistance or impedance. When we're dealing with loads, when we reconfigure them, we reconfigure the total amount of kVA that they're going to be putting in and out. In order to do this type of starting, what we do need to have is we need to have a motor that's going to go and have all leads exposed. So I'm going to need to have at least 6 or 12. I cannot do this off of a 3-lead motor, nor can I do this off of a 9-lead motor. You should be familiar, we've got 3, 6s, 9s, and 12s as being our common configurations for motors. We know that anytime that we have got a 3-lead motor, that there's already going to be an internal connection. And that anytime we've got a 9-lead motor, we are once again going to have an internal connection or connections. It's either corner connections if we're looking at a Y, or it's going to, at a Delta, or it's going to be a center star if we're looking at a Delta. Same with on this one over here. It's either going to be corner connections if we're looking at a Delta, or center connections that are going to be pre-done if we're looking at a Y. So because we don't have the option to reconfigure those are buried inside, we have to scratch those. We don't have the option to go and utilize them. We're only going to be using 6 or 9-lead types of motors. We're going to do, inside of here, we're just going to look at a 6-lead motor, because the 6-lead motor is just easier for us to go and understand. If it were a 12-lead motor, all we would have to think about is that we would take our windings and we would configure them so that basically, this would be my seriesing. If I had these, and then I would go through from, instead of going 3 to 6, my 6 would have ended down here. We then go off on the next ones here, 7, 8, 9 that we would then have, and then 10, 11, 12 would be my terminals that I would go and have. So I would have, terminal 3 through 6, 9 through 12, etc. off of here, and I could be either seriesing those or paralleling them depending upon what the voltage is. That's just 3-phase motor connections that we would be dealing, based upon the supply system that we would be looking at. What we're looking at over here is we're looking at just the simplest one over here, so you can apply that, to a 12-lead if you need to. Let's talk about just the theory about why we see so much less power when we're working with a Y or a Delta type of system. Over here, we've got a Delta connected system. Now, there's going to be a couple things we're going to note that are going to stay the same. One is going to be the voltage that we are connecting to. We have to keep it the same. The connection that we're bringing in to the motor is going to always be the same. It's just going to be how we reconnect it inside of here that's going to be changing. So I'm always going to see the same value of voltage. I'm also always going to go and see the same value of impedance on my actual loads themselves. And they give us an impedance for these calculations over here. They say, look, we got a 10 ohm type of impedance. And if we've got a 10 ohm type of impedance, what is the total amount of current that I'm going to go and have inside of here? What is the total amount of power that I'm going to go and have inside of here? All of these other things that we can calculate off of it. For us, knowing that this is a Delta, and if we know that we've got a line value, we know that our E phase is going to be same as our line value. So it's going to be 208. So we could go and figure out the total amount of current going through this winding over here by just taking my value of E phase, dividing it by my value of resistance, right? We don't have to use root 3 because we're only working with the values that are going to be inside of here right now. So I would just go and take my 208 divided by my 10 ohms of impedance, which is going to get me to 20.8 amps. So I know I've got 20.8 amps that is going to be going through there, 20.8, and it's going to be meeting up with another 20.8 over here, and then together they're going to go and join, and according to Kirchhoff's current law, they're going to go and add up. But because they're 120 degrees out of phase with each other, they're going to go and add vectorially. We're going to get to that 36 amps, and we could get to that 36 amps the exact same way by just going and taking our value of I phase, which would be 28 times my root 3. Just take 20.8 times root 3, you end up at 36 amps. So we could go and figure out what our total amount of watts would be that we would be delivering out of this thing. Now, I'm not going to go too far down the watts path. We can come back from the watts path for a second there, just because when we're looking at the watts, we are going to go and see different amounts of power that we would go and have out of our delta compared to our Y. Now, we understand that we're doing reduced voltage starting, not actually reducing the line voltages that we have over here. We're just reconfiguring the load, so it's going to react different off that. And I'm not really that concerned about the value of watts that I'm going to go and have out of this motor at, full delta compared to, startup Y. What I'm really concerned with is this value over here, because this is going to go and determine my inrush amount of current, right? If I've got a motor that's got an inrush current that is going to go and be 5 times that, that's basically 5 times 40 over there, which would be about 200-ish amps, so somewhere up in that range. It's going to be a bit less than 200-ish amps, maybe like 180-ish or something like that. I don't know, I'm not doing the actual math, but it's going to be somewhere around 180-ish amps that I would have if I had a 5 times inrush for the squirrel cage design of motor that I'm looking at. So that would be a significant amount of current to go and run into this motor. If I would take the exact same windings and the exact same lines, so the same value of voltage, we're not changing our value of voltage, and if I would take the exact same 10 ohm impedances over here and I would reconfigure them now inside of a Y type of configuration, I'm going to go and change my values of current. If we take a look at this, we would see that we are going to go and have, based upon the 10 ohms over here, we've got a 2-way line to line, which means that my phase value is going to be 120 volts. So if I were to take 120 volts, divide it by 10 ohms, I'm going to go and find out that I would go and have 12 amps that would be going through this winding. And when we take a look at that 12 amps, we see that the 12 amps doesn't add up with any of the currents, right? It's the only current that's going through that lines. Therefore, we are going to go and have 12 amps that is now going to go and exit from here. Once again, if we're dealing with the exact same motor, remember these are not just, loads, these are motor windings we're talking about. If we had the motor that had a 5 times that we were looking at, wrong with it. If we had 5 times the amount of FLA is going to be what our inrush is based upon the motor design class, we would also have that off of this, except now we would be looking at doing 5 times 12 amps, which is only going to be a value of about 60 amps that we are going, it is going to be 60 amps that we are going to go and have for our inrush. 60 amps of inrush looks a heck of a lot better than 180-ish amps of inrush that we would get from this one over here. Really, this is going to go and, tell us a little bit about the torque as well. We see that, what we normally have is 36 amps. When I reconfigure this one over here, we see that my full load current is going to be 12 amps. So I'm looking at 1/3 the current when I do a startup like this. If I'm at 1/3 the current, that means that is going to be directly related to my startup torque value, right? So if my startup torque value was a design class D that had 300% torque, 1/3 of 300% would mean that I'd be starting at 100%, even though I'm doing this, reduced inrush that I'm having. If I've got something that is going to be, let's say, 150% torque that I'm going to be starting up, I would be looking at 1/3 of that would be what I'd be starting up under. So I'd be starting up under about 50% torque. As long as the torque is sufficient to get the load started, by all means, go ahead and do it. And once again, we just got to reiterate the fact that anytime we're looking at doing any type of reduced voltage or reduced current startups, that we are always have to be aware of the fact that if I cannot start it underneath, the full across the line, I would not be able to start it like this. So you'd have to actually size, this is 150% startup. You'd have to say, would 1/3 of that, 50% startup, be good to go for me to go and start this thing? You'd have to compare that with those torque charts, those curves that we saw, looking at those design classes. Okay, because it is going to be 1/3 that we're going to start on, this is going to be a hard and fast value. It doesn't matter how you do your math or what the motor is going to go and be, you will always end up at 1/3 of your startup torque for these. We are going to be limited to light motor loads or motor loads that can be started unloaded. They give you examples of fans. Fans aren't moving a lot of air when they start up, so they're going to have a light load, or unloaded centrifugal compressor pumps. We will use these on large scale motors, but we would have to have bled the system off. You know, if you've got a compressor that already has pressure in it, you wouldn't be able to go and start this up with that. It would just be too light of a torque that we would go and have. We also have to be very aware of how our overloads are going to go and operate. The rating of our overloads are going to be based upon the phase values, because ultimately we are reconfiguring our values of our overloads as we're going in and out of these. Or sorry, not reconfiguring our value of our overloads, but what we are doing is we are reconfiguring our location of the overloads. It'd be really hard for us to keep those same overloads in the line in the proper position at all times. So what I need to do is I need to go and base my overload upon the phase value of the delta connected motor. And I'm going to go and see that I'm going to go and place that always just in line. Ultimately, my overload is going to be in line with every single one of these over here is going to go and have its overload section placed in line when we're at our full operational state. Doesn't matter whether we're going to be looking at open transition or when we are going to go and be closed transition. Okay, let's start with our open transition one. Open transition is a relatively straightforward connection over here. Once again, anytime that we are dealing with open transition, we are going to get a momentary torque dip where we're just kind of coasting through off of how fast we managed to get that motor operating before now. And then we're going to have to, hope that that's going to be sufficient for us to run this thing, or for the load to not stall it out until we can make that transition to our running phase. Let's start by taking a look at our control circuit over here and examining a couple of important things. First of all, we see S and 2M over here have got a mechanical interlock as well as they've got a electrical interlock that's going to be across here. We get double interlocking off of these ones because we are looking for protection. Because really, if I did not go and have those two interlock, S and 2M, I could go and put myself into a really, really bad situation where if I managed to go and fire these two simultaneously like this, what we would see is that we would have a direct line-to-line short here, as well as another line-to-line short simultaneously happening here, as well as another line-to-line short simultaneously happening here, like that, right? We're shorting all of our lines together if we manage to operate these two at the same time. So we don't want that to happen, so we've got that mechanical and electrical interlocking that we are going to go and have on both those. Let's go and take a look at our controls for this one. We'll examine the types of control components we have over here, and then just, their relationship that they're going to go and have with each other. Over here, we see that we've got two of these. They are going to be on delay type of contacts over here. This is a normally closed, time to go and open. So when we apply power, it's going to time, and then this one's going to pop open. This is going to be normally open, time to close. When we apply power to the timer coil, it's going to wait, and then it is going to go and kick that thing closed. For the rest, I've got a timing relay that also has an instantaneous contact. Oops, sorry, that one doesn't have the instantaneous. That's the one I'm thinking about. I've just got the timing relay here with these. I can leave that at that. I do have my 1M, which is going to be my main contactor that I'm going to go and have. And that main contactor is going to go and have an interlock over here. And I do have my actual overloads themselves. The overloads themselves, remember that they are just creating heat that is going over to affect that normally closed 95-96 contact that we're going to go and have. So even though these are connected inside of the phase of the motor, as we mentioned before, they're still going to go and affect this thing on the actual control circuit itself. Still provide us with that needed overload type of protection. Let's go through our control circuit. As we go through our control circuit, we're going to do that thing where we build ourselves a timing diagram so that we can go and jump through our motor operation. We're going to start by building the timing diagram, then I'm going to take the timing diagram into this one over here. We see that at the instant that I close my start switch, well, actually we'll wait. At the instant, we'll start by saying this is as far as power can get through normally. At the instant that I go and close my start switch, I'm then going to be able to go and pass power through to my TR. And I'm also going to be able to pass power through to my 1M, which is going to seal me in. And I'm also going to go and pass power through to my S. So at the very instant of startup, we'll do stop, start, and then I'm going to go and have TR, 1M, S, and 2M. That's 2, 2, 2M that we are going to have. So at the instant that I go and apply my start, just do a quick little button press over here, it is going to go and apply, put a dotted line down here, it is going to go and cause my TR, so I press this, TR is going to go high, as well as my 1M is going to go high, as well as my S is going to go high. And all of these are going to go and stay high until my timer finishes its time. Okay, we're going to go and have a time that's going to go and operate inside here. And when this timer finishes its time, we're going to go and get other operation that's going to go and happen. So we'll just carry these lines through up until the timer does its time, because we know that none of these lines are changing. It's a low there on the 2M. When my timer finishes, what I'm going to have happen, remember that we've got this interlock over here, is that I'm going to go and have to wait for this coil over here to open, my TR. So this one is going to go and open. It is then going to depower this one. And when this one depowers, it recloses this one. This would have been closed as well. These two operate at the same time, the timing relays, which would then power on my 2M. So we're going to go and see this operations, interlocked operation that we are going to see where my timing relay finishes its timing. As soon as it finishes its timing, the very first thing that's going to happen is it shuts off S. So we'll see S, that's going to go and drop first. And then slightly after S drops, it closes its normally so closed set of contacts when it depowers, which is then going to go and power on my 2M. So my 2M is just going to be a hair behind my S. 2M is then going to be powered on, and at that point we're going to be in full operational running mode. So now we can go and carry the rest of these lines, out along here, we'll carry them along here, and then the very last thing that we'd have to look at is then what happens when we press our stop. We'll take the stop over here, we'll drop on the stop. When we drop on the stop, it is going to go and interrupt current flow to TR, interrupt current flow to 1M, and interrupt current flow to 2M. So we're basically going to go and see, as soon as we apply the stop, that the entire circuit over here, anything that's high, is just going to go back to being low. That one's going to drop, that one's going to... You see my drawing looks, pretty janky when you're taking a look at it because I'm working off of just freehanding this over here. I highly suggest that, if you are going to be doing your timing diagrams, that you keep a little bit of lined paper. Lined paper is super, super easy for this. You just write your what you're looking at in between two lines, and you go high, low, high, low. Just make sure you're skipping a line in between so you don't end up overlapping your lines. Now that we've gone through creating the actual timing diagram off of this, why don't we go through on the actual motor? So I'll just erase all of these, and we'll jump onto the actual motor operation. We're just going to use this timing diagram over here to go and define which of these are going to go and close at any given time. So we're going to start by bringing our power in as far as power could proceed before it would go and hit an open set of contacts. Okay, so we'll open that, we'll open that, we'll open that. That's as far as power can make it into the circuit. What we'll next do is we are going to go and say that the instant that we press start, we see that a couple things happen. There's going to be TR. I see I've got no TR contacts on here. That's going to close. 1M is going to go and close. That's going to be all of these ones over here. And S is also going to go and close, which is going to go and be these ones over here. What does that give us for a power path? Well, if I take a look, I see that, I'm just going to trace these through one at a time. This one goes through the overloads, through the winding, and up to that star point. This one goes through and up to there. And this one goes through and up to there. And I see that all three of these are joined together, so I have got my Y type of connection. So I'm going to go and have a Y connection. That's what we've just done right over here, is we've just followed this line through here right now. That's my Y connection. Then I'm going to be timing, and then we're going to have a couple of things that are going to happen right close to each other, but that are not going to be happening at the exact same time. Remember, my S fires a slight bit ahead of my 2M because we have got that interlock that we see on them down here. So I'm going to get to the point now where my timing is going to go and finish, and the very first thing that it is going to do is it is going to go and fire the S coil off. And when it fires the S coil off, that is going to go and drop this out, drop this out, which means it's going to interrupt. And at this point, each of these paths no longer has a complete path for current flow. So I'm going to have no power that is going to be going through my motor. I don't have any complete path at this point. S drops out on both of these, and then when S finishes dropping out and recloses over here, we saw that 2M was then going to go and close. And when my 2M closes, I see that I have got this one, which is now connected through from line 1 to line number 2. It's not going to make it through that. Those two are open. I see that I've got this one, which is connected from line 2 over to line 3. And I see that I've got this one, which is connected from line 3 back to line number 1. This is a delta type of connection. So we do have just a open transition that is going from one to the other. We started in Y, which is going to be at a third of my startup torque. We then transition that thing into delta, which is going to go and give me my full torque out of this motor itself. Basically, it's going to be the length of whatever this section is, however long it takes for this interlock section to go and react. That's going to be how long this motor is going to be without power. Really, really fast, but if you got a heavy load, it might be, not that you're actually going to go and see a torque dip off of that one as well. You'll note as well that, once again, when we're looking at this as a closed connection, if I look at just my A phase, I see that that current that is going through there is going through my overload, and it's only going through the actual phase itself. It doesn't share any current with anything else, which means that I'm going to be using my phase value of current. If you go and take a look at your motor nameplate, the phase current is just going to be what it would be if it was connected in Y. It's going to be the lower value of current that would be listed on the nameplate. Okay, that's our easy cheesy one. The next one that we're going to go and have is going to be a closed transistor, and the closed transition type of connection. And the closed transition is going to be more complicated because we cannot short out coils, but we do have to go and have a way that we can close across some coils as we're making that transition from one to the other. So we're going to go through the closed transition. I already pre-drew a timing diagram because we're going to go and chase that timing diagram across from component to component inside of here, and then we'll come back to this main drawing over here. The very first thing that we're going to do before we look at the timing diagram is we're just going to go and take a look at our power diagram, and we're going to note that there is inherent danger in some of our connection. Once again, the inherent danger would be if my 2M were to go and close and if my 1S were to go and close, we would go and see line-to-line values of current that could go and be shorted, right? We would see that one that could go and short out. We would see this one that could go and short out to line 2. We would see line 3 that could short to line 1 through it. It would just be a mess. We would have this dead short across all of our lines, which would go and destroy a lot of components. So what we do need to make sure is that they can't operate at the same time. This is going to be done through the use of, once again, a mechanical interlock. That's going to be represented by the dotted line, and an electrical interlock, which means that this one's going to have a normally closed up here. This one's going to go and have a normally closed contact up there, so that we can't fire either one of these until the other one has completely settled back into its de-energized state. Other than that, we're pretty much the same through a lot of our control components. We're going to do the same thing where we are going to go through, we're going to develop the timing diagram, and once we've developed the timing diagram, then we are going to go and transfer that to our actual power diagram that we're going to have off of here. And I've even gone and redrawn this thing, so that we can see transition to transition, just what those connections themselves actually are. A couple things to note off of here. We've only got one timing relay that is going to go and have one set of timed contacts over here. It's normally open time to close. And we see that when that timing is going to finish that, I've got a bunch of purple lines over here. The purple lines are just indicative of the fact that we have got interlocks. We're going to go from one to the next, to the next, to the next. It's going to be the sequence of controls that we need to go and see happen as we're going through. So let's go through this timing diagram development, and then we'll go and start applying it to the actual power motor diagram that we're going to have. We're going to start with the start button. That's what we always do. We can also start with taking our power and just putting it through on our controls up to where we know that it's going to be stopped by open sets of contacts. So the second that I go and press my start push button over here, I'm going to go and have power that is going to pass all the way through here, and I'm going to seal that in through an instantaneous contact off my timing relay. Once again, timing relays can have multiple different types of contacts that are going to come off. Some are timed, some are instantaneous. As soon as it goes and seals itself in over there, it is also going to seal this in over here, which is then going to go and apply power through those which are closed out to 1S. Power is going to wait over here. And because 1S has gone and closed, it is going to go and apply power through to 1M. And because 1M closes, it is going to seal itself in over here like that. And because 1S has powered up, as soon as 1S did power up, this opened over here, so we are blocking power from getting through to my 2M coil. Let's transfer all of that down here onto this. What we see is that we had pressed the start. When we pressed the start, the timing relay went high. Because the timing relay went high, we saw that the timing relay applied power through to the 1S. The 1S goes high at the same time as our start. And we see that when the 1S goes high, it closes in here and instantaneously applies power to the 1M as well. There is a tiny little bit of lag going from one to the other. You know, in reality, it would be this one, and then this one. But it's going to be so fast, it's basically instantaneous, and we're not really that concerned about these ones in the same sort of interlock sequence as we are going to be later on. So that's the three of those that are going to go and fire on initially. So we're going to go and have it operating then in this state for the first little bit, where we are going to go and see this one high, and this one high over here, the 1S and the 1M, that are really going to be the motor contactors that we are going to see initially pulled in over here. Then what we're going to go and have happen is our timing is going to go and finish, and when our timing finishes, it's going to go and put in a sequence, and it's going to be a really rapid sequence that we're going to go click, click, click from one to the next, where we're going to go and have contacts that are going to go and control the next set of contacts off of each of these. So let's start with our timer finishing up. The very first thing that the timer does when it finishes up is it is going to go and apply power to 2S. So now we are going to go and have power that is going to be put through to 2S. When it applies power through to that 2S, what it's going to do next, let me just see if I can erase these 1, 2s, and 3s without grabbing everything. Oh, lovely. So it's going to apply power through to the 2S. As soon as 2S has got power applied to it, it is going to go and operate its sets of contact, which is going to be this contact up here, which is going to go and drop out 1S. So we see that the next thing that happens is going to go and be, this should still have power up to there, 1S is going to go and drop out. That's my next thing, and we see that indicated over here, right? 2S fired on, which then went and dropped out 1S. When 1S goes and drops out, it is going to go and open up its sets of contacts. Put that one back up there. It's going to open up its sets of contacts. So it's got a set of contact over here, which is simultaneously going to go and close this set of contacts, which is going to go and power up 2M. So I'm going to go and see, following through into my timing diagram, 1S has operated, which has now gone and brought power or applied power to my 2M that we are going to go and see. 2M is going to go high, and then when my 2M goes high, when we provide power here, that in turn is going to go and open up that set of contacts over there, which is then going to go and drop out everything that's going to be downstream of it, which is really just going to be this 2S that we are going to go and have over here. So 2S is then going to go and drop out, and we see that on our timing diagram over here that 2S drops out. And at that point, we're now going to be running just with this inside of our circuit. Sorry, I erased that line there before, but the 1M does stay in the whole time. Really, we see that once we have gone through this little sequence over here, the two main contacts that are going to be running are going to be main contactor 1 and main contactor 2. And then we have all of this powered up until such time as we go and press our stop button. Sorry, press that stop button. When I go and press the stop button, it is going to interrupt current flow to my TR, which is going to interrupt current flow to the rest of my motor, which is going to bring everything back down to its default states. We see that over here. I press the stop goes low, and I see that everything else is going to go low once again off that timing diagram. If we follow that through on this diagram over here, we can just start this thing by saying we've established what the sequence is. Now let's take that timing diagram, let's apply it to this. we see that the very first of our contactors that are going to turn on are going to be my 1M and my 1S. So it's going to be this and this that are initially going to go and turn on. What we should see at that point is that we have got power that can be passed through from here up to a start point, passed through this one up to a start point, and passed through this one up to a start point. So I would go and have this thing connected in Y. That would be my initial startup over there. The next thing that's going to go and happen is my timing. So it's going to start accelerating under Y. I then run my timing until I hit this T point. Once the T point happens, the very first thing we see is that my 2S is going to go high. So as soon as my 2S goes high over here, we're going to go and see that we have got a resistor that is going to go and be connected across. Now, if I take a look at this, I see that I do have paths for my current flow to go and follow through. We'll just follow this one maybe with a marker off of this one. But if I take a look at this, I can go and run from here down through my coil, and then I can go back up through here, and I can run from here across to this one. Or I can run from here, I can go across to this one. So what I'm seeing is that I can run from this line, I can go through here off of these resistors. We got resistors inside here. We're going to cover this thing a little bit more in depth later on, but it's preventing us from having a short circuit. Because if I didn't have this short circuit inside of here, what I would see would be a short circuit from here. Not from that one there, but across from that one that I would then short circuit out to the other line. If I didn't have this resistor, we would really see a short circuit that would be happening across from here to here, but because we have this resistor in line with it, we no longer have to worry about that sort of short circuit. So that's our very first thing that happens, is that 2S is going to go high, it's going to go and close. The next thing that's going to happen is going to be 1S that is going to go and open. When 1S goes and opens, what that means is that we are going to go and have interrupted paths of current that are going to now be running through a series over here. So 2S is closed, 1S has opened. Let's just follow this one through. I would see that it goes through my coil up here, and then it would go and travel through like that. So I'm basically going to have a coil in line with a resistor just for a split second, right? That's all we're seeing this in here is for just a split second. Then I'm going to have a coil through with a resistor. The other ones are all the same, so I'm not going to trace those through individually. Next thing that happens after my 1S goes low is that my 2M is going to go high. So now what I'm going to do is I'm going to go and bring these all high. When I do bring these all high, I am now going to go and have my lines. This path of current that's going through the resistor is going to go and divert, because now it can go through like this. It can bypass that. There's still going to be another smaller amount of current that is going to go and travel through the winding and back like that, but it's going to be so small. The bulk of our current is really going to go and transition over to this one over here. And then the very last thing that I'm going to go and see happen, my 2M has closed, is then that my 2S is going to go and open. And that 2S, when it opens, it eliminates that small little green path that we just looked at over there. And at this point, every single one of my coils is going to be connected across from line to line. I can take a look at the next coil here. We can draw that one with the green. You see that it connects across line to line. And we take a look at our last one over here, and we see that it connects across line to line as well. We are going to be operating in full delta mode over there. Let's go down into this. This is going to be my same timing diagram. We're just going to step through it. We're going to eliminate the entire control. This just shows, and I've taken all those. These are not inside of your binder. You know, you can go and draw this stuff out yourself. You got lots of room underneath, you know, the final paragraph over there. But we see that at my first connection over here, I'm going to go and have my TR that goes high, but what we're really critical about is 1S goes high and 1M. That's what we're looking at this point. 1S and 1M, and so we see that we have got this connection that is going to go and be made. It is a Y type of connection. From there, we then go and add in our next thing. This is now happening after we go into the timing. When we go to the timing, we should see that 1S is high. We should see that 2S is going to go high, and that 1M is going to go high. 1M is closed, 2S is closed, 1S is closed, and what it's showing us right now is that we have got a set of parallel connections over here. We can really follow this through as being a fact that we have got a parallel motor connection, and just for a split second, we've also got, in parallel to that, we have got, and they're sharing the same neutral point, a parallel resistance connection over here. Like that. So it's as if I've got a set of resistors connected in Y across the same power supply as what my motor is operating in. That's this second point that we are looking at over here. From there, we are then going to go and move into our third one, which is going to be this one here. So 1S is going to go and drop out, but I'm going to go and see that my 2S is going to go and say high. My 1M is also going to go and say high. So I'm going to lose that little connection that's inside of there, but I'm going to go and keep 2S high, and I'm going to go and keep 1M high. And if I take a look, now I would see that I'm going to go and have connected across here, the only path for current for this one is to go through like that. The only path for current for this one is to go through like that, and the only path for this one is to go through like that. So basically I've got a delta type of configuration. That's what's just happened over here, is that we've kind of reconfigured this into a series delta where I'm going to go and have resistance and inductance in line. This is basically what we are looking at for this same change over here, where the 1S has gone and opened. It is through that opening up giving us this type of a connection over here, where only 1M and 2S are going to go and be high. And that's going to be this point right over here, where only 1M and 2S are going to go and be high. The next thing that we're going to go and see happen is that my 2M is going to have to go and become high. So when 2M goes and becomes high, what 2M is going to do is it's going to short around my resistors. So now I'm going to have full power that's going to be going into here. And I'm just going to have this short that's going around that resistors. We're still going to have a small amount of current that is going to travel through there, but it's not going to be much that's going to be taking that path, because the bulk is going to take the path of least resistance. What we are looking at over here is we are looking at this point where 2M is high, 1M is high, that's this one here, and 2S is still instantaneously high at that point. When that finishes up, because we're going through this context, this tick, 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 and it's all happening over top of just, a second or so. The very last step that we see inside of here is where my 2S goes low, and it's just going to be 1M and 2M that are going to go and be high. We see that over here, 1M and 2M that are going to go and be high inside of these connections over here. Bringing us to a full delta type of operation. It's a pretty cool system, really, when you go and take a look at it, watching the way that this transitions all the way through, where we start this thing up, and we're going to start this thing in a Y, and then we're going to go and, maybe build a parallel resistance Y, and then we're going to go and transition over into a series, RL type of circuit just for a split second, and then we're going to short around the resistance, and then we're going to go and remove the resistance altogether by opening up that one set of contacts. It's a lovely but insanely complicated setup that we are going through here as we're moving from one set of contacts to the other. Once again, timing diagrams really are going to go and become so critical. It's so easy to otherwise get lost and build yourself into what you think is going to be a short circuit inside of the circuit or things like that. If you cannot read these, I can read this one through years of practice without having to have that timing diagram that's showing me click 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 that the steps that this thing is going through. But it is still easier for me. It's not that I can't do it off of this, but I'd way rather just build this, because it's only going to take me a couple minutes to go through this control circuit, build this timing, and then carry that over to my contactors and actually understand what's going on inside of that circuit. Okay, that is it for my Wye-Delta starters.